Mosfet Circuits at Dc. Hello everyone, my name is Rafael, I'm an electrical engineer, and in this video I'd like to show you the solution of 4 exercises concerning Mosfet circuits at DC. Let's go to the first exercise. Exercise number 1. Design the circuit of the figure so that the transistor operates at ID equal to 0.4 milliamperes and VD equal to positive 0.5 volts. The NMOS transistor has VT equal to 0.7 volts, nu NCOX equal to 100 microamperes per volt squared, L equal to 1 micrometers, and W equal to 32 micrometers. Neglect the channel modulation effect. Okay, my friends, let's go. Let's go to the solution. Okay. The design requirement is that VD is equal to positive 0.5 volts, and since VG is 0 volts, then VD is greater than VG, what grants that the transistor is operating in the saturation region. Saturation. Okay? Knowing this, we shall use the expression for the saturation region. And the expression is ID, this current here that's going to flow through here, okay? ID is equal to a half of nu N COX W divided by L VGS minus VT squared. This is the expression for the saturation region of operation. What we need to do is merely to put the values here. For nu NCOX, we put this value. For W over L, we put 32 divided by 1. And VGS minus VT squared we don't yet have. And we are going to comply with the requirement of ID being equal to 0.4 milliamperes. Then we do just that. Okay, then it is going to be 400 microamperes times equal to a half times 100 microamperes per volt squared, 32 micrometers divided by 1 micrometer, and then here we use VGS minus VT squared. Okay? This is the expression. We are going to solve for this, and we find that VGS minus VT squared is equal to 0.25 volts. Okay? If we continue developing this, we're going to find that VGS minus VT is equal to 0.5 volts. And since VT is 0.7 volts, we find that VGS is equal to 0.5 volts plus 0.7 volts, which is 1.2 volts. Okay, this is the value of VGS. And then we have the values, okay, VD we already know, okay, it is a requirement. VD is 0.5 volts, okay. Since VG is 0, it is grounded here. Since VG is 0, then VS has to be equal to negative 1.2 volts, okay? So these are the values of the voltages. VD is here, 0.5 volts, VG is here, 0 volts, and VS is here, negative 1.2 volts. Now let's calculate the values of the resistances RD and RS. RS will be equal to VS minus VSS divided by ID. Okay, let's interpret this. VS is here, VSS is here. The voltage on top of this resistor is Vs minus VSS, and the current that flows is ID. We can use Ohm's law to find this, and we calculate it to be, we simply use the values we calculated. Vs is minus 1.2 volts. VSS is negative 2.5 volts, and ID, as the problem required, is 0.4 milliamperes. And then if we conduct this calculation, we find that RS is 3.25 kilo ohms. Likewise, we can calculate RD. RD is here. RD is going to be equal to the voltage drop here on top of this resistance, which is VDD minus VD divided by ID. Okay? VDD is here, VD is here. the voltage on top of this resistor is VDD minus VD. And if we substitute VDD 2.5 volts and VD 0.5 volts divided by 0.4 milliamperes, we get the value of 5 kilo ohms. Okay? These are the values of the resistances that we wanted to calculate. Now, let's go to exercise number 2. Design the circuit of the figure to obtain a current ID of 80 microamperes. Find the value required for R and find the DC voltage VD. Find R and VD. Let the NMOS transistor have VT equal to 0.6 volts, nu NCOX equal to 200 microamperes per volt squared, L equal to 0.8 micrometers, and W 4 micrometers. Neglect the channel length modulation effect. Okay, let's go. Let's solve exercise number 2. The solution. Okay. Because VGS is 0, you see that the gate is connected to the drain. Alright, VGS is 0. Okay? VG is equal to VD. And this grants the saturation region of operation. And we are going to use again the expression for the saturation region of operation. And then, knowing that it is in the saturation region of operation, we use that ID is equal to a half of nu NCOX W divided by L VGS minus VT squared. Okay? ID we know is 80 microamperes. 80 microamperes equal to a half of, we substitute this value here, 200 microamperes per volt squared times 4 micrometers divided by 0.8 micrometers. And here again, we use VGS minus VT squared. We are going to solve for this term here. And if we conduct this, it is easy. We find that VGS minus VT is equal to 0.4 volts. And since VT is equal to 0.6 volts, we find that VGS is equal to 0.4 plus 0.6, which is 1 volt. Okay, this is the value of VGS. Okay? Keep this value here, okay? It is important. VGS equal to 1 volt. I'm going to erase it here for the next calculation. And as As VGS is equal to VD, and as Vs is 0, we know that Vs is 0 because Vs has been grounded. Okay, then Vg is equal to Vd equal to 1 volts. Okay, we have calculated all the voltages. Lastly, we need to calculate the value of the resistance. R is going to be equal to VDD minus VD divided by ID. Okay? The voltage on top of this resistor here is VDD minus VD. Okay? On top of this resistor, VDD minus VD. If we divide by the current, we get 3 volts minus 1 volt. 3 volts here, 1 volt here, divided by the current, 80 microamperes, and we find the value of 25 kilo ohms. Okay, this is the last result of exercise 2. Did you guys understand? Then let's move on to exercise 3. Now let's go to exercise 3. Design the circuit of the figure to establish a drain voltage of 0.1 volts. What is the effective resistance between drain and source at this operating point? Assume Vt equal to 1 volts and the Kn prime W over L equal to 1 milliamperes per volt squared. Okay, let's go. Let's do it. The solution VG is connected to 5 volts. Okay, so VG is 5 volts. And VD, this is a requirement of the exercise, VD has to be 0.1 volts. Then VG is greater than VD. Then we conclude that the Mosfet is operating in the triode region. The Mosfet is operating in the triode region. In this way, we are going to use the expression for the triode region, which is different from the expression of the saturation region. Okay, the expression for triode is ID equal to Kn prime W over L VGS minus VT times VDS minus a half of VDS squared. This is the expression of triode. Now we simply substitute these values, okay? Then ID, we want to calculate ID, is going to be equal to this, okay? 1 milliamperes per volt squared. VGS S is grounded. The source is grounded. Then VDS is VG, 5 volts, minus 0, which is 5 volts. And VT, the problem gave VT as 1 volt. VDS, VD, this is a requirement, VD has to be equal to 0.1 volts. And since the source is grounded, VDS is equal to 0.1 minus a half of 0.1 volts squared. All right? Have I made a mistake? No? Is everything right? Let's continue then. And if we calculate this, it is easy. We find a value of ID approximately equal to 0.4 milliamperes. Okay? This is the value of this current here. Approximately 0.4 milliamperes. With this value, we can calculate this resistance here. Let's do it. Let's put it here. Now I can erase here. So RD, one more time, as we did before, RD is equal to VDD minus VD divided by ID, okay? VDD minus VD is the voltage on top of this resistor. If we divide the voltage by the current, we get the resistance. VDD is 5 volts. VD, the problem gave us 0.1 volts. ID, we just calculated 0.4 milliamperes. And then we find a value of approximately equal to 12.3 kilo ohms. Okay? We are dealing here with approximate values. You don't need to be precise here, okay? Because you're going to need to put up with the values of resistors that are available in the market, okay? And since you're not going to find a resistor like this, you can choose RD to be equal to, okay, which is going to be available in the market, RD equal to 12 kilo ohms. And now we need to calculate the effective resistance between drain and source. This is the last question of this exercise. The effective drain to source resistance is RDS. This resistance is within the transistor, okay? This is not outside as there is resistor here. This resistor is in the circuit. This resistance is in the component. This is the resistor of the resistance of the channel inside of the transistor. It is going to be equal to VDS divided by ID, which is again approximately equal to 250 ohms. We are dealing with approximate values here, okay? Okay, my friends, this is the solution of exercise 3. Now we can go to the last one, exercise 4. Now let's go to the last exercise. Exercise 4. Analyze the circuit of the figure to determine the voltages at all nodes and the currents through all branches. Assume Vt equal to 1 volt, Kn prime W over L equal to 1 milliamperes per volt squared, Rg1 10 mega ohms, Rg2 also 10 mega ohms, Rd 6 kilo ohms, Rs 6 kilo ohms. Okay, let's do it. Let's calculate the voltages. Since the current that goes here, the gate current is 0, okay? The gate current cannot be different than 0. It has to be 0. If the gate current is greater than 0, you've blown the device, okay? And you have to replace it. Under normal operation, this current here is 0. Okay, since the current is 0, to find this voltage here, Vg, we can simply apply a voltage divider rule here. And then the voltage divider is going to be Vg is equal to VDD Rg2 divided by Rg1 plus Rg2, okay? To find this voltage here, first of all, what is going to be the current? Just to get you a gist of this, the current is going to be VDD divided by Rg1 plus Rg2. VDD divided by Rg1 plus Rg2. If we multiply this current by Rg2, we get the voltage. So this is the idea behind the voltage divider. And we substitute the values. 10 volts, 10 mega ohms divided by 20 mega ohms. And in this way, we find that Vg is equal to positive 5 volts. I'm gonna put it here, okay, 5 volts. Now we are going to calculate the rest, okay? See that Vg is greater than Vt, okay? Vt is 1 volt and Vg 5 volts. Whenever it happens, whenever Vg is greater than Vt, the device is going to conduct. Okay, there is a channel for current conduction. So we know that the device is on because Vg is greater than Vt. We know that the device is on. But we don't yet know whether the device is operating in triode or in saturation. We don't know this yet. All we know is that since Vg is greater than Vt, it is conducting. The channel is open. We are going to assume saturation, okay? We are going to assume saturation. If it turns out to be saturation, then we did everything right. And if it is not right, we are going to discover that it is operating in triode. Then we are going to assume, okay, it's going to be an assumption. At first, we are going to assume that the device is operating in saturation. So let's go. VGS is equal to VG minus VS. Obviously, okay, we are assuming saturation already. VG is 5, we already know. VG is 5 volts. But we don't know yet VS. VS is here, okay? Here, VS. We don't yet know. What we can do is to multiply the current ID, okay, the current that's going to flow here, ID, we multiply ID, which is going to be milliamperes, by this resistance here, 6 kilo ohms, okay? This is going to be on top of this, VS. VS is this current, okay? The current that goes down through here times the resistance, which is 6 kilo ohms. Okay, then we are going to use this expression here, minus 6 times ID. Okay, this is the expression that we're going to use in the saturation region. Okay, let's save it here. VGS equal to 5 minus 6 times ID. Let's save it here. We're going to use it. In the saturation region of operation, we use this expression for ID. ID equal to a half of Kn prime W over L. VGS minus VT squared. Okay, but in the place of VGS, we are going to use 5 minus 6 times ID. And then we use that ID. We are going to substitute these values here that the problem already gave us. It's going to be equal to a half of 1 milliamperes per volt squared times 5 minus 6 times I minus 1. VT is equal to 1, and this is squared. And if we develop this, we are going to find this quadratic equation, 18 times ID squared minus 25 times ID, okay, plus 8 equal to 0. All right, this is the quadratic equation that we get. It's easy to solve this, okay? Everybody that has gone to high school knows how to solve this. Okay, so we are going to solve this equation here. And if we solve this equation, we are going to find two values. We are going to find a value for ID equal to 0.89 milliamperes and a value for ID equal to 0.5 milliamperes. If you use this value for ID, you are going to discover some inconsistencies, okay? And this value here is just right. then we are not going to use this value. You can check yourself, okay? Do it yourself. Use this value here and you're going to see that everything that we calculated does not hold true. Okay, there will be some inconsistencies. Then the only value that we're going to work with is this one here. And this is the only one that makes physical sense. And if we use this value here, we are going to find here that Vs is going to be equal to 6 kilo ohms. Okay, we're going to find the value of Vs is equal to 6 kilo ohms times the value of the current we just calculated. And it is equal to positive 3 volts. Okay, so Vs is equal to positive 3 volts. Now let's calculate the other values. We have to calculate Vg and Vd. Okay? VGS, here we are going to use this expression VGS is equal to 5. We can use this expression here, okay? But we can use that VGS is equal to Vg minus Vs, okay? Vg is equal to 5 volts and Vs we just calculated 3 volts, and then Vgs is equal to 2 volts. Okay, then these 2 volts. Now what we need to do is to calculate. Okay, we already have Vg, we already have Vs, and we need to calculate Vd. The only voltage that we need to concentrate on now is Vd. Okay, Vd is going to be equal to 10. Okay, Vd is here. All right, Vd is here. Vd. Vd is going to be equal to Vd is going to be equal to 10 minus this voltage drop here. Okay? Vd is going to be 10 minus the voltage drop here. So Vd is 10 volts minus the voltage drop on this resistor here, which is 6 kilo ohms, which is the resistance of the resistor. And if we multiply by the current, we get the voltage drop. And then we find that Vd is equal to positive 7 volts. All right? And since Vd is greater than Vg minus Vt, okay, 7 is greater than 5 minus 1, okay? Since this holds true, Vd is greater than Vg minus Vt, we are indeed in the saturation region of operation as we supposed before. Okay, my friends, these are the exercises that I wanted to show you the solution. I hope you guys enjoyed the video and the solution and learned from the video. I am a teacher. If you guys want to book a lesson with me, use my WhatsApp number, guys. Goodbye!